Okay, then let's start with the lecture today. So the distinguished lecturer at the Max Planck Institute for the Science of Light is, to remind me, is thought for the thought leaders of the field and the pioneers in their fields. And so it's my great pleasure to introduce Scott Diddams, who holds the Robert Davis Endowed Chair at the University of Colorado Boulder, where he is a professor of electrical engineering and physics. His domain is precision spectroscopy and quantum metrology, nonlinear optics, microwave, photonics, and ultrafast lasers. And he received his Ph.D. degree from the University of New Mexico in '96, and was then a postdoctoral fellow at JILA, NIST, and the University of Colorado. And after that, he became a research physicist, a group leader and fellow at NIST, and moved then in 2022 to the University of Boulder. And here he has also the role of faculty director of the Quantum Engineering Initiative at the college. So he has many pioneering results. Some of them is he built the first optical frequency comb in the lab of Nobel laureate John Hall. And throughout his career, he has pioneered the use of them for optical clocks, tests of fundamental physics, novel spectroscopy, and astronomy. And he has many, many publications, more than 750, and conference papers, and also invited talks. I want to mention some of the prizes that he got. For instance, the Distinguished Presidential Rank Award, Presidential Early Career Award in Science and Engineering, the OPTICA C.E.K. Mees Medal, the IEEE Photonics Society Laser Instrumentation Award, and the Rabi Award. And we are very happy to welcome you here at the Institute in Erlangen, and we are looking forward to your talk.
Thank you very much for the... Thank you very much for the very kind introduction. Seems like the gain is too high. I don't know if it can be turned down a little bit. Yeah. Okay, I can kind of talk loud myself, so often I don't need the microphone. So yeah, Brigitte, it's a real honor to be here. I mean, this is a very distinguished institute and university here in Erlangen, and so you say this is a distinguished lecture, but I feel very fortunate to be here and be able to share some of the things that we're doing in Boulder with you today. So you already heard a little bit of my background. I work with optical frequency combs, of course, a long heritage of that technology here in Bavaria, and from the group of Ted Hensch in Munich. And I'm gonna, sometimes when I give talks, it's as instructional for me giving a talk or presenting a talk as it might be for you. And so what I'm going to tell you about today is kind of my foray, into quantum optics with optical frequency combs. And I wasn't trained as in the background of quantum optics. I sometimes say I'm a semi-classical guy trying to find my way in the quantum world. Quantum is all the rage these days, but there's nothing new. I mean, this is the 100th year of quantum mechanics. There's not really anything new in the theory of quantum mechanics, but the devices, the tools, the technologies we have enable us to do new things, and particularly to control light and matter in new ways. And I think that's why there's a lot of excitement in this area, in this field. And so what I'm going to tell you about today is a little bit of my foray into that. So I think, first of all, as Brigitte mentioned, I spent most of my career at NIST, the National Institute of Standards and Technology, which is kind of the PTB, the Physikalisch-Technische Bundesanstalt of the US. And it's in Boulder, but a few years ago, in 2022, I moved across the street. And if you've been to Boulder, the institutes are very close. And so it wasn't a big move physically, but it is an interesting move in that now, although I was trained as a physicist and think of myself as a physicist, now I'm in the College of Engineering. So it's kind of interesting, maybe it's reflective a bit of the opportunities in quantum science these days, is that, as I already insinuated or implied, developing new tools is as much the excitement as, say, discovering the basic quantum science. So that's a picture of Boulder in the winter, in the summer, with a big football stadium, American football, and this is part of the group of the people I get to hang out with every day. And I would say that, yeah, that's one of the real pleasures of my career, is being able to work with young people, being able to work with really bright colleagues at the University of Colorado. So some of the things I do is related to clocks and precision timing. That really stems from my work at NIST. Frequency comb spectroscopy, I'll talk some about that. I work a lot with astronomers. I find these biggest questions that still face us as humans, a lot of them have their roots in astronomy. So I enjoy taking some of my tools and using those in astronomy. And then all of my work is kind of founded on nonlinear optics, ultrafast laser phenomena, and more integrated nonlinear nanophotonics. So you'll see bits and pieces of those research activities throughout the talk. So I think today what I want to tell you about is, first of all, I know it's a broad audience, so we'll speak quite generally at the beginning and just make sure people know what frequency combs are or how I think of frequency combs, and then tell you a little bit about my view of quantum metrology. And then I'll give you a few examples where we are exploring frequency combs at and beyond established quantum limits. And part of the message I want to get to you today is that actually it's quite challenging to even define what the standard quantum limit is when you move into a new domain. And the new domain would be multi-mode light, short pulses onto photodetectors. These are photon sources, so quantum limits are usually related to shot noise. But it's even hard to define what that quantum limit is when you start talking about this. So this has been a bit of an adventure for a decade of trying to understand clearly what the limits are, so we even know, are we, or can we, or will we surpass them? And I'll give you a few examples of that in these areas here. So it's a very tutorial slide, but I just make sure everyone's on the same page as to what I do. I work with these sources called optical frequency combs, which are arrays of perfectly evenly spaced modes in the optical domain that you could describe with this very simple equation. And without knowing how you would generate that, and in fact there are many platforms now that you can generate such combs, you don't have to know anything about the technology or the physics of generating them. If they are equally spaced and phase locked together, if you sum up those modes a la Fourier, you get a train of short pulses. And so it's this beautiful connection between frequency and time domain in which you get to live with in this field of optical frequency combs. And I would say not only does it allow one to connect like optical frequencies to microwave frequencies, but a big impact of this field is also being able to synthesize light and to make optical fields with controlled phase. And you control that phase in the microwave domain, and you can realize that in the optical domain. So that's a big impact of this field, not only for precision metrology and spectroscopy, but also for folks, just down the road in Munich, another Nobel Prize in attosecond control of fields and matter. So all frequency combs are generated in cavities, and this is how we would create, say, a superposition of modes. These could all be like the standing wave modes in a cavity. And again, if we have a mechanism to phase lock them, to define a well-defined phase between the different modes, if we add them up, they create a short pulse that circulates in that cavity. And at the output, if this is like a Fabry-Perot and a little bit of transmission, then it's a train of pulses that comes out, and you already see that dark line is a microwave frequency that is phase coherently linked to those optical frequencies inside the comb generating cavity. So all frequency combs have a means to enforce this phase synchronization between the modes, and all frequency combs need a cavity to provide coherence long term, and it's really a storage mechanism. The light that goes around, the cavity provides a memory, so that after one round trip, we know what happened, 10 nanoseconds or a picosecond ago, and onto the microsecond range. So this provides the way of reducing high frequency noise. There's many platforms. I won't really talk about the platforms, but there's work here and other places, and continues to be evolution of different ways to make frequency combs. And so the technology is a lot of fun to work with. Ranging from erbium fiber lasers to electro-optic type devices to fully integrated Kerr combs. This last one is quite unique in that a thing that's really interesting about the Kerr nonlinear process for making Kerr combs is there's no energy storage in the medium itself. And so it's only the interaction of the light fields inside there, and that you can send in a continuous wave beam of light, constant intensity, and at the output, magically you get pulses. This is still, I think, one of the most wonderful discoveries in this field, and actually Pascal was involved in the early days in Tobias Kippenberg's group, working out details of that. So yeah, that is a revolutionary technology, frequency combs are. I think in this slide, what I would just like to impress on you is kind of the functional operation of a comb as a gearbox, or as a clockwork, or as a synthesizer. And combs, as I already told you, are not mechanical gears, but a beautiful thing about them is they function exactly like a mechanical clockwork like that, in that you can take microwave frequencies in and use this as a multiplication gear to get optical frequencies out. And here you see it, each little wheel. If it was in this cartoon picture, you can see the continuous wave light associated with each of those modes. You can operate it the other way. That's how we make clocks. We would control one of these modes coming in. It divides down and we get microwaves out, so we can count the uncountable in that way. If optical cycle is on the order of a femtosecond, we can accumulate 1 million of those seconds or 1 billion of those seconds and get a microwave cycle out with precise control. And I can't emphasize that enough, is that gear picture, you can know exactly the gearing ratio if you want, and it's perfect as far as we know. We've tested, myself and others, I quit it when I got to 20 digits. Other people continued going on to 21 digits or so. It's a perfect clockwork. So that provides a really revolutionary ability to phase coherently connect microwave and optical domains. And as I already noted, it provides this electrical control of optical fields. Maybe there's a lot on this slide, but I just emphasizing this connection between optical and microwave domains. So this slide shows history along the bottom and frequency here. And these are kind of human-controlled realms of the electromagnetic domain where we are developing and controlling oscillators. And it was here in Germany, the work of Heinrich Hertz, the person who first created an electromagnetic wave, propagated it across the room and measured it. Spectacular experiment. And that blossomed and led to everything that drives our modern society now. Communications, navigations, phones, it's all here, but going up to maybe gigahertz or tens of gigahertz range. It was in 1960 that the laser was developed, first human-controlled coherent source of light. And similarly, there was an explosion of applications, and I think probably best exemplified by optical communications. If you think about it, it's stunning. You have a Zoom conversation. I had several last night with people in the US, and it's, through the fiber under the ocean, it was like I was just right there. And so these laser technologies have had huge impact on us. It was the frequency comb that phase coherently united these two domains. And so I think what that allows us to think about are how could we take the best of optics and use it for microwaves or RF? How could we take the best of the RF domain and transport that to the optical domain? So it opens up a whole new paradigms of how we could manipulate, use electromagnetic fields in one domain for the benefit of the other. Okay, so that's the few slide background on optical frequency combs. How about quantum metrology? What does that mean? Well, let's just start very simply. It's the use of quantum objects for measurements. And oftentimes those could be single particles, single atoms, single ions, single photons. But they can also be interesting things like macroscopic electrical circuits, quantum dots, NV centers. I saw molecules in the basement today here, as single quantum objects. Okay, and if we can control those, and as I already mentioned, a lot of the excitement in quantum, and there's a lot of buzz, probably overhyped in quantum, but okay, if you're inside the field, maybe let's live it a little bit and enjoy it. We don't know how long it will last, but it genuinely does give us unique measurement capabilities for different fields, for length, position, gravity, and even unknown fields, like, dark matter, dark energy. We still don't really know what those are, but the very precise tools of quantum metrology might give us insight into being able to make, to figure out what those unknown fields are, if they would couple to electromagnetic waves, for example, or couple to atoms or an electrical circuit in some way. So I think the precision that quantum metrology provides, it's like a microscope that can see with 18 digits of precision, at least in the case of clocks, that might give you a unique view into the unknown universe. I would say that the real secret sauce of quantum, of course, is correlations or entanglement that give us an advantage, or I like to think of it as in measurements, what it really gives us is a speed up. Like, quantum doesn't make things more accurate. It just enables us to measure things more quickly and more, and if you can measure something in a second now, but you could do it in 1/10 of a second, or if it took you a year to make a measurement and you could do it instead of a month, that can be a real advantage. So I think that's what everyone's looking for in this field of quantum measurement and quantum metrology. And I guess the message is it's really hard. And if you want to achieve true quantum advantage, and many of you are familiar with this LIGO experiment. One of the pioneers, I think a remarkable paper, if you haven't read the work of Carl Caves from the 1980s, he wrote down the recipe of the noise in an interferometer and how to overcome that noise with squeezed light. And so he wrote that down in 81. It took almost 4 decades before quantum light was truly introduced into these interferometers and expanded our view of the universe, at least as a gravitational wave observatory. So I like this quote from Carl Caves. He was a professor of mine at University of New Mexico. Don't ask quantum optics to save you until you spent the last penny of your billion-dollar budget on classical solutions. And okay, if you knew Carl, he said this near the end of his career, and he said, I get tired of, I get tired of people asking me when we're going to have a quantum computer and when quantum is going to do this for us and that for us. And there's definitely amazing things that we can learn and discover by controlling quantum particles with quantum measurements, but you shouldn't expect it to come for free, I guess. Maybe that's the message. It's a lot of work. So this is my view. I don't know. You guys aren't, it's Bavaria, you aren't too far from the Alps. So this is the story you hear in mountain climbers is, well, why are you climbing the mountain today? And it's, well, I don't know, it's there, right? And so why are we going down this hole? It's because it's not there, and we don't quite know what's at the bottom. And so that's part of the discovery process in learning with optical frequency combs. Where could they bring a quantum advantage to a measurement problem? And it's really a question that I live with every day, and I'll, in the rest of the talk, give you a few examples. Okay, so let me move on to this second part of the talk where I'll briefly tell you about photodetecting pulses, low noise microwaves. This is a bit of a story of we don't know where the quantum limit is, and actually it was a surprising story. It's more than a decade old, but we continue to work in that. Very simple systems, optical heterodyne. How do you describe heterodyne with a comb from quantum mechanical theory? So we've been working with theorists on that. And then I'll tell you about the squeezing part of my story and these techniques of dual comb spectroscopy with squeezed frequency combs where we can see some advantage. So if you think very simply with optical frequency combs, there's It's photons, okay? So I'm talking about measurements with photons. There's basically three things you can do, right? In some sense, you might be disappointed. You'd say, oh, I want to do more. But you know, if you try to drill down and say, fundamentally, what are the types of measurements I could do with an optical frequency comb? There's essentially three things, or these are the three things that I work on at least. There's optical heterodyne. We use the heterodyne between CW lasers to build clocks. So one of these lasers, let's call it FB1, that could be the laser that is steered to an atomic transition to make an optical clock. That clock frequency then controls the comb and gives you that down conversion, that gear picture I presented, okay? But we can also go over here to another side of the spectrum and compare against another clock laser, another atomic transition. And so this is how we do fundamental measurements and fundamental comparisons between very precise optical frequency standards. And ultimately those beats look like sine waves, but there's fuzz on them, and that fuzz ultimately is from shot noise. Pulse rate detection, you know, the down converted, this Fourier superposition of all these modes gives this pulse train, and when we detect it, there will be some fundamental jitter on them. And if we want to make super precise timing systems, ultimately that will play a role. And then in another realm, if we want to use this comb as kind of a digital sampler to measure molecular spectra, there's a point where the uncertainty in how well we can measure the amplitude of those modes is limited by quantum mechanics. So let me tell you just quickly about this pulse rate detection problem. It's something that I've worked on for now nearly 25 years. And that's this process of optical frequency division, where it's basically an optical clock, but clocks in general are focused on how I keep track of time at seconds, hours, minutes, days, years, long time. But there's speed of light is fast. And so if you're going to use light or electromagnetic waves in practical communications, sensing, LiDAR, radar systems, it's actually the short time, you know, milliseconds, microseconds, that matters. And so we came up with these techniques for just starting with a very stable laser, the narrowest line with the most stable electromagnetic oscillators that exist, and using the comb as a down converter. And so we go from 500 terahertz to 10 gigahertz in this phase coherent fashion. And a big benefit of that is that the noise from our spectral density of phase fluctuations on the optical get divided by this big factor n squared. So we can technologically get a huge reduction in phase noise. And if we, you know, just some punchline numbers, if we use this to generate 10 gigahertz signals, these signals can have femtoseconds of timing jitter compared to kind of the very best, couple orders of magnitude better than what you could achieve with the best electronic oscillators. And we've, you know, this is a phase noise power spectral density plot, so the spectral density of phase noise fluctuations in a 10 gigahertz signal that we generated in this way. And we've identified some of the fundamental noise limits, at least practical. Some of these you can cool. You can get, you know, if you take things down to lower and lower temperatures, you get rid of thermal noise. One on F detector noise, you can remove some of that with cooling also, but the shot noise floor is something that is just intrinsically related to the photons that hit this photodiode here. And so we spent quite a few years looking at this, and Frank Quinlan was a postdoc with me who worked on that and now leads a group at NIST himself. But here's the interesting observation that relates to the question of what is the limit. It turns out that shot noise floor, it changes depending on the duration of the optical pulse you put on the detector, okay? And you know, if you know the standard formula for shot noise, there's pulse width isn't in there. It's just 2Q or 2EI, right? And I is the average photocurrent. So I can have an average photocurrent. It tells me what the shot noise is. But here I'm telling you it's different. It depends on the pulse width. And actually, there were seeds of this idea from the gravitational wave community. Those guys studied everything. And they studied what it looks like when you put modulated light on detectors. And the observations we made and the simple theories we developed came out of that. But the The thing is that the continuous wave shot noise limit is like up here, and as we drop the pulse duration, we can win 5 dB. And you might say, oh, it looks like you're squeezing or there's nonlinearity, but it turns out it's not squeezing at all. It's just because the pulses are, you know, the photons come in little bunches, and it's not stationary process like shot noise is. All the shot noise equations assume that it's time stationary, but here we're providing bullets of light. And so this is called a cyclostationary process, and this leads to an imbalance in amplitude and phase noise. And a very simple picture is a long pulse, the blue one, or the red pulse here is a shorter pulse. And the noise, if you look in one quadrature, that's the zero crossing, the phase quadrature, as you shorten the pulse, the shot noise, the fuzziness here, becomes a smaller and smaller fraction. And so near that zero crossing of that quadrature, the integrated noise can be much lower. This is a simple time domain picture. In the frequency domain, you can, we in this paper we wrote, reference here, you can see kind of our frequency domain interpretation as well. So I just point that out as something that was a little bit surprising as I started to ask myself, like, well, what are the quantum limits? And they weren't defined, they weren't well defined. And so there still needs to be these kind of things taken into account. There's more situations like this. I'll highlight one of them, but as you deal with frequency combs or pulse sources of light, the quantum noise can be different than your textbook continuous wave illumination. Let me tell you a little bit about this situation, optical heterodyne, because that's a really impactful one. In Boulder, we've built clock networks, and you can see, you know, without understanding all the details, that there's usually an atom or an ion. Aluminum, ytterbium, strontium are the quantum references. And then at each interface, there's the comb. It functions like a gear. So this is 267 nanometer, 578 nanometer, 698 nanometer. If they were in terahertz, these are separated by hundreds of terahertz, not to mention, you know, some kilometers. Here, by the way, is NIST, where I used to work, and now I work right over here. But you have this huge bandwidth, and you have to phase coherently connect them. So that's, the comb works in that way to do that. A few years ago, we published a paper, our first results on this optical clock network. We called it the Bacon network. And these were our numbers. And I think these are some of the most accurate numbers that humans have ever written down, that are not 1 or 0. There's a lot of experiments people do where they say, oh, I got 1 or I got 0 and I proved it to part and 10 to the 18. But in terms of numbers with 18 digits, I think these are quite unique. And what we're looking at is the ratio between, say, aluminum and ytterbium, aluminum and strontium, ytterbium and strontium, these ratios of the quantum states, okay? One thing to note is to make that measurement takes time, okay? And things weren't always perfect in these measurements. And like your experiments, you know, things kind of start running at 4 in the afternoon, right? And then you stay until midnight or whatever, and you get the good data then. And tomorrow it doesn't work, but next week it works again. But if you aggregate the data that went into this, it's kind of a few months worth of effort. And the averaging for these kind of measurements goes as the square root of the averaging time. So if you wanted to add another digit, and let's just say it was a month, you don't have to average 100 months if it was the same duty cycle. Okay, so this is a little bit of a made-up example, but the point is, as the numbers get smaller and smaller, the uncertainty gets smaller and smaller, you're going to want to speed things up somehow. And technologically, we can do that if we make the lasers more, you know, better technology. If we show up at 8 a.m. instead of, you know, noon, maybe that helps. But anyway, there's some technological things, but fundamentally you're limited by this averaging time. The quantum statistics of doing the measurement limit that averaging time. So we would like to speed that up. And there's lots of different efforts to try and speed it up. But one of them relates to this interaction right here, where I take a continuous wave laser and interfere with the frequency comb light. Okay, so I'm kind of on the frequency comb side, so I'm interested and worried about that. So that brings us back to very fundamental, basic properties of interfering fields. And if there's bedrock, homodyne and heterodyne for quantum optics. And Gerard Loix isn't here today, but probably others in the room know this field way better than I do. But here you would have signal of interest coming in and then some coherent state. And you want to know, what do you get at the output of the detector? Well, I was working with a theorist, Josh Coombs, he's in Australia, and so we came up with a clever term, comodyne, where now if our signal of interest coming in, and this could be the CW laser that's heterodyning with the local oscillator, the comb, we want to be able to understand rigorously what would be the quantum limit for that. And so Josh helped figure that out. And this is a bit of a theory slide. I'm not a theorist, so I'll talk about it maybe in a slightly different way. The problem is mode matching. And if you know something about quantum optics, you know that modes are very important. And the problem, whenever we're taking a signal, an unknown signal in, and trying to interfere it with these trains of pulses, if you just think in the time domain, they're terribly mismatched, right? You have light on all the time in your continuous wave laser, and then boom, boom, boom. There's short pulses coming in from time to time that are kind of sampling it, this cyclostationary process. This is not mode match from the quantum point of view. But with Josh's help, we developed this rigorous quantum description of the operator that could cover this. So now with that theory, we know what the realizable quantum limits would be. And just as one example, in this CW laser heterodyne with a comb, some early measurements, and this is a student of mine, Eugene Tsao, who's actually now at ETH Zurich as a postdoc. But a key idea is if you have pulses from the comb and then nothing in between, and then another pulse and then nothing in between, well, let's just gate out, let's get rid of the measurement time in between. Okay, and so all that's going on in that measurement time in between is light making shot noise on your detector, so let's get rid of it. And people in quantum optics have used this trick in different ways, but here we use it to show in this heterodyne how we can win and up to 20 dB SNR. So our measured signal to noise, if we take the total shot noise, is up here, but if we could remove the shot noise when we aren't measuring, the heterodyne quantum limit would be 20 dB lower. And our first try at this, we quickly won 8 dB, and the 8 dB, it could have been better, but we still needed better temporal mode match between our, it's a little more complicated gating out, it's a whatever, 100 femtosecond, picosecond pulse, so there's also electronics involved in that, and so that waveform, we don't have perfect mode match for that. But this shows a path forward for, significantly improving signal to noise in these heterodyne beats. And also, again, this point on, what are we really aiming for? What is the ultimate noise floor that we could achieve? So that's a simple example in those types of networks. And particularly, I think it's interesting for low power transportable comb systems. We're going to want to ultimately soak every dB out of the signal to noise. So we use all of our classical tricks. This is just a classical one, gating, before we employ novel quantum states of light. Let me just, I won't talk a lot about this, but I wanted to just give you a flavor of our next network. This is a really fun experiment that we're working on in Boulder. And that is to do gravitational sensing with, we call it quantum sensors of time, fancy word for clocks, okay? So here's the experiment. If you've been to Colorado, you know that there's kind of these nice, we call them the foothills right outside Boulder, but you can't even see the big mountains behind it, which are about 4,000 meters or so. But we, working together with Andrew Ludlow, Laura Sinclair, we've been building a network where we take a transportable clock to the top of one of these mountains. This is Mount Blue Sky. It's pretty rough. We had to had to buy a generator. We had to, install Starlink, so we have Wi-Fi up there. The problem is you can't see from here down to Boulder. Boulder's over here. So we have to go with and you can't string a fiber there. So we have actually a free space link 50 kilometers down to the roof of a building in Denver, and then the light goes in fiber back to Boulder where it's compared against a stationary clock. And there's a lot of details here. You see some little combs here and there, but again, kind of the gear work underlying this comparison is frequency combs at these different nodes. And what we want to test scientifically is the gravitational redshift. So this clock up here should appear to tick faster compared to the one in Boulder. And with this type of elevation difference, we could test this, make the most precise test of Einstein's GR theory ever. I think that's interesting. I think that's going to be one of those tests where we get 0. You know, Einstein was right, I think. But I think what's kind of more interesting is this one, is that we are introducing and trying to validate new techniques to measure the shape of the Earth. And so wouldn't it be wonderful if these types of systems could ultimately be compact, could be moved around, and they could tell you, oh, there's something moving under the ground there, that there's, you know, maybe there's an earthquake, maybe there's volcanic activity under there, there's something changing with the geology of the Earth. It could also tell you where water would flow. This field of geodesy, the measurement of the gravitational potential, the shape of the Earth, its most immediate impact is water obeys gravity. So if you're in a floodplain, you would be able to say, oh, the water's going to flow that way and not this way. With centimeter type precision, that's what the clocks will be able to tell us, is the difference in these elevations at the centimeter level. So that's ongoing. In fact, just this past fall, we were able to close the link. We can actually have a phase coherent comparison over that link. And if you're going to the clock, I don't know if anyone here goes to clock conferences, but there's a meeting in the Netherlands next week, and some of my colleagues will present results there. It's a fun experiment. Yeah, it's really quantum engineering. You know, you need cranes to put things on rooftops. Yeah, there's mountain goats. There was snow that shut us down. I think this is other than in space, there's cold atoms in space. I think now this is the highest cold atom experiment on Earth. That's the ytterbium lattice clock at 4,500 meters. So that's pretty cool. Yeah, let me now come to the final topic about frequency comb spectroscopy. And here I need to introduce a little bit how we do spectroscopy and why that's impactful. So comb picture with molecular absorption looks like this. The fingerprint of this field or of this atom or molecule gets imprinted on the comb. And actually that step is pretty easy. That has impact in a lot of different areas, as the cartoon shows here. But the challenge is how to read out that spectral information. You might have thousands or hundreds of thousands of modes involved, and what are we going to do? Build a spectrometer that tracks all those different modes, or how are we going to get the information from each of those modes? We use a technique in Boulder. A colleague of mine, Nate Newberry, pioneered dual comb spectroscopy. Actually, I should say pioneered. The first experiment in dual comb spectroscopy was done by Stefan Schiller, or the proposal for it. And then there was work in Max Planck Institute where there's some early experiments done, but Nate really worked out the theory and our understanding and implications, our application of this. So the idea is we use a Vernier type technique to get the information off the comb teeth. And this Vernier picture is maybe best seen in the frequency domain, where pairs of optical comb teeth have a unique one-to-one mapping from the optical domain to the RF domain. So this pair of comb teeth makes a beat here, this pair makes another beat, and so on. And these are very precise RF beats, built-in precision from the optical domain. And that way we can measure, say, changes in the amplitudes of these comb teeth that some absorbing medium would put on them, and we could do that quickly. We could do that over broad bandwidths. Turns out that it was just a few years ago that that in these experiments that we finally reach the shot noise limit. And this is what one of these experiments look like. This is measuring carbon monoxide. And here's a beautiful spectrum of carbon monoxide and model and a fit. And the residuals are shown down below here. And those residuals, you might say, well, that doesn't look white. That doesn't look like shot noise. You can see some variation. The variation is due to the fact that the power of the light changes across the spectrum here. But we verify this is the shot noise limit. So then what do we do next? We want to try to do something with the quantum light or quantum nature of the light to squeeze or to manipulate the light into a different quadrature so the noise would be lower, say in the intensity quadrature than the phase quadrature. So this is a very old field. I don't think I have to go over it here, but I just want to respect the people who have worked in this. You know, I guess I was in grad school when this paper, oh no, I was an undergrad when this paper came out. You know, I was getting my bachelor's degree. So there's people who've worked in this area in a very long time, including folks at this institute or around the world, right? And so again, like what could possibly be new? What could possibly be exciting? And I think it's our ability now with these multi-mode frequency comb sources of light to introduce some new capabilities, not to teach you something new about quantum optics. There's, you know, the type of squeezing we do is soliton squeezing, so also very well developed. Gerd Loix has papers in that area as well. But I had to go back and learn a few tricks there and a few things that people had learned in the past, and I just want to point those out to you. One thing is we do this squeezing in optical fiber. So this is a picture from Prem Kumar's paper, but maybe a piece of optical fiber. It turns out that with Kerr squeezing, and here's like the simple, the phase that is involved there. With Kerr squeezing, your little ball of uncertainty gets squashed into something that looks a little bit like a crescent or a banana. But if you were to measure along this axis here, it turns out it's still the standard quantum limit. And that's because it's a photon number preserving process. And so you don't have any quantum advantage if you measure here. And this is what Kumar taught us was, well, we actually need to displace this field in one direction. So it's kind of like rotating this crescent a little bit. So now we can measure truly along its minimum axis. And so what we did is we implemented these ideas with frequency combs, and then we introduce a displacement here, and then we show how you can read this out with a frequency comb as well to do this type of dual comb spectroscopy. So there's a simple picture of the squeezing we can achieve, and whether you displace the strong field this way or that way, takes you from squeezed to anti-squeezed. And we're doing these measurements, I would say, there's a lot of photons in the field, 14, 15 milliwatts of light. It's about as much light as good detectors, or at least the good detectors we have, can handle. So we can definitely make squeezing, and this squeezing is measured, this is measured just with a single detector. It's not like a homodyne detection, but we had a shot noise limited light source, so we could see that directly. We didn't have to subtract out any technical noise. But the interesting question then is to ask, if we interfere these fields in this dual comb technique, the dual comb technique has the time domain interpretation that the two frequency combs walk across each other, kind of like a Fourier transform spectrometer or the output there. The question is, how do we describe that from a quantum picture? And the interesting thing, or the take-home message, is that most of the time in this measurement, the two pulses are not overlapped. And so we're measuring the intensity of one kind of against vacuum. So it's like an intensity measurement. And so our coherent state that would be going into the interferometer is often just measuring against the vacuum state here. And so if we replace this coherent state with a state that's squeezed, this psi variable here representing some level of squeezing, then we can see the entire noise level in the measurement drop. So we did that, and it's a simple experiment. This amplitude squeezed frequency comb, that's done in nonlinear optical fiber. We have to rotate, apply a small displacement to that field to get it, to line it up as I described to you. And then we interfere it with a separate comb at a different repetition rate. And we record interferograms. We put some molecules in there, hydrogen sulfide. And the geometry we used was quite interesting, is that we can have detection here where the hydrogen sulfide sees the interference of these two fields. And then in this arm, we have a reference spectrum, no gas, so we can normalize out the background. And when we do that, and we do these kind of rigorous fits, here you see the residuals. Okay, this is the anti-squeezed, the standard quantum limit, if we want to call it that, and the case where we have the squeezing, and you see the residuals drop. And I think what's interesting here is we get this information across 2,500 modes all at once, covering about 2.5 terahertz of spectrum. There's seminal papers in the work. Jeff Kimball, Eugene Polzik, colleagues, they did squeezing squeeze light spectroscopy back in the early 90s with 2 gigahertz of tunability. So this difference between kind of a factor of 1,000 in the bandwidth we can cover practically instantaneously. Or this is 5.6 kilohertz difference, so we get a spectrum essentially every about what would that be, 500 microseconds or so. We get a new spectrum. So we can measure fast over broad bandwidths. That's one power of this dual comb technique. This is the enhancement, the quantum speed up. So these are the uncertainties, the uncertainties of the fit residuals, and you see the 3 cases here I showed on the previous slide. And this shows this factor of 2 speed up. If we can drop the noise by square root of 2, we win factor of 2 in the averaging time. And so that starts to be significant. If your measurement took a day, now it takes half a day, right? Or if it took, an hour, now it's half an hour. 3 dB is nice. We'd like it more, and yeah, we're working on that more now. Let me just say in the last few minutes a few words about what we're studying now. Is like I told you that most of the time the reason this works is we're measuring far from the overlap between these 2 pulses, but there is time when the pulses do interlap, and we call this zero path difference. This is where you get the strong interference between the 2 cone pulses. So what's going on there? So what we've been devising now are ways to use one comb to displace that squeeze comb. Okay, and so these are the pictures of the interference between the successive combs. So we might have the squeeze comb and a coherent comb, and they walk across each other from pulse to pulse. And then what the detector measures is the integral of that overlap. And so for each of these, we get a kind of a point on our interferogram. And in the kind of quantum space, what we see is that we're either measuring here, this is the constructive interference case, here's the destructive interference case. So we're able to sample this entire radius or circumference of this displacement here, and do that very quickly. And in between are these cases where we get anti-squeezing and squeezing. So this gives us now, in general, we would have shot noise on these traces, but then there's special places in between where we should see anti-squeezing and squeezing on the interferogram. So we came up with a nice idea actually for measuring both the noise and the signal at the same time. So we take our signal and we divide it, and we measure the interferogram, the strong signal, in one region of the RF spectrum. We take another region, high pass filter, and we measure the shot noise in another region of the spectrum. And we can digitize both of these at the same time, and these are what some of the data look like. This is the interferogram, and these are scaled by 70 or so. We call this the noise gram. We see the noise go up and down and up and down. The red level is shot noise, so it dips below there. If we quantify this in terms of a squeezing parameter, we see that the interferogram in dark black, we get extremely high signal to noise on these interferograms, like the highest you can achieve with interfering 2 frequency combs. And then here we see the noise going up. And here's the interesting thing is that at some quadratures, right, at this zero crossing, for example, the noise is squeezed by 2 to 3 dB. At the other quadrature, so this is on the, what's that, the up slopes, it's squeezed. On the down slope, it's not squeezed. And this, this paper, by the way, it'll come out in PRL here in just a few weeks. But what this gives us is a tool for precise timing, because we can hope what we can do next is locate on one of these peaks. And in this network, for example, I showed you the free space network, pulses flying 50 kilometers through the air. This type of capability would enable us to measure a zero crossing at a place where there's less noise. And so in principle, this could lead to systems that could have lower pulse timing between them. So we're excited to explore that. I think I'll leave you with kind of a fun picture in the lab. So this is really ultra-fast quantum noise in real time, or you could call it a quantum oscilloscope. Probably an overused term, but let me show you what you're seeing is you're seeing here the interferogram, the interference of these two pulses. That's what was shown on the previous slide. But then here's our noise-gram, and so far out in the wings you see shot noise, but then as the oscillations come in, you see the noise shoot up and down. It's a little bit hard with this is like a cell phone camera of the sampling card in the lab, so it doesn't have, that's why it's jiggling around a little bit. The hand wasn't so stable, but in between here are these regions where the noise drops down. So we can see this. We think this is also quite interesting for things like tomography, and in fact, we're been reading papers from this institute on vacuum squeezing and techniques to make Sagnac loops to do vacuum squeezing, because we want to now make vacuum squeeze combs and do ultra-fast or do fast tomography on them. Okay, so this could give us a tomographic measurement, and we want to study, like, I think it's quite interesting to study this in a very high nonlinear regime, where you could get, maybe we get divergence from Gaussian states or Gaussian states of noise. So I think I'll leave you with that. Yeah, I told you a little bit about frequency combs, where they butt up against quantum limits, where those quantum limits still need to be defined better, and some first experiments where we're actually trying to push beyond those. Yeah, these are some of the things that we're working on. I have a big interest in thermal light heterodyne spectroscopy for astronomy. I don't have a chance to talk about that today, but we're very interested in building VLBI, very large baseline interferometers that would work in the near infrared or mid-infrared region of the spectrum. That's a very impactful area for astronomy, and we want to know what would be a frequency comb as a local oscillator can already bring something quite interesting. I'm quite interested to try to understand what kind of a quantum local oscillator would be the most valuable in those scenarios. So yeah, longer term, I think squeeze combs in different wavelength regions, we get lucky, hydrogen sulfide absorbed around 1550, but most of the interesting molecules or systems we want to look at are at different wavelengths. So we've got to figure out how to translate quantum frequency comb light to other wavelength regions. I think it's a long-term goal of bridging the gap between quantum modes and frequency comb modes. Frequency comb modes, as I described, are phase coherently linked. Quantum modes, maybe they are. In some cases, people make these cluster states, but in general, these come from OPOs below threshold, and it's not clear that there's really a phase coherent relationship between, say, the multi-modes that you would get in a Kerr resonator like Pascal's generating, and how that would relate, sub-threshold, how that would relate to, the modes that I know and love and described here. So I think I would love to work with theorists who have broader, stronger, deeper knowledge of those kind of questions than I do. And then I think a really interesting problem would be, what kind of transduction could we do in combs? Could we really, a comb is a perfect transducer of classical light. I told you it works to 21 digits, right? It works exactly like that gearbox picture. but could we take a quantum state of light at one wavelength and transduce it to another wavelength randomly? And people have done this, of course, with second harmonic or with DFG. But here, what if I wanted to go from atom A to atom B, where they are not harmonically related? I think these are really interesting fundamental questions and experiments to work on. Okay, so with that, I'll thank you again. You know, US may not look so friendly from the outside, but I just want to let you know that anytime you want to come visit Boulder, I'd welcome you. And yeah, what's that?
You have to get through the passport.
You got to get through passport control. I can't help you there, I'm sorry. It's a direct flight from Munich to Denver. We're just outside of Denver, you know, 45 minutes or so. So anyway, thank you again for the invite. Thanks for hosting, Brigitte. And yeah, thank you all for listening. And it's a pleasure to be able to share with you today.
Thanks a lot for this very pedagogic talk and the exciting results. I'm sure there are questions. I let Pascal start.
Thanks a lot, Scott, for this very inspiring talk.
Yeah.
I have one question regarding this clock link between the mountain. How do you get the transition from the free space into the fiber part, or how does the laser link work? And is it all optical? And the other question is, which part is more noisy, the free space part or the fiber part?
Oh, that's a good question. So okay, it's all optical. Okay, so down here in the stationary lab, the clock, that clock transition is in the yellow region of the spectrum. The frequency comb coherently translates that to 1550, which then goes in the fiber optic link out to here. And then at this point, another frequency comb translates the CW light into pulses. So this is pulse light, and it's bidirectional. In terms of what's noisier, they don't tell us. It's kind of interesting that we got access to the fiber, but they don't tell us where it goes. I think the free space link is definitely noisier, especially because, you know, the noisiest part of the atmosphere is right near the Earth, where there's a lot of thermals, and so we're kind of poking up through that. But this link can be made. I mean, it's used with like an 800 nanometer and a kind of pointing laser and a CCD to get you close. And then once you get that, then you can lock on with the 1550 signal itself. Yeah, that's Laura Sinclair's work. That's not my work. She's the one who really pioneered that. Yeah. Yeah.
Thanks a lot for the great talk. I have a question regarding the slide when you mentioned the shot noise reduction as a relation of pulse duration.
Yeah.
Right here, so like if we think about repetition rates and like gigahertz or kilohertz combs, would you reduce or increase your shot noise?
I guess you know, let me say what this limit is here, we call this the CW shot noise limit. So this is 2EI, so I guess that's calculated from the photocurrent. So probably if you went to kilohertz combs, I mean, well, I don't know, it's kind of hard to make a kilohertz comb. I know people have done that, but I guess it would depend on whether you get a reduction here or how much reduction is relative to that CW light that you put on the detector. So probably it's easier to see with higher repetition rates. This was done with gigahertz lasers. So I guess I don't fully know the answer to your question. That's why I'm hedging a little bit. But I think at kilohertz rates or megahertz rates or sub-megahertz rates, it might be hard to see this, just because you would probably blow up the detector with a high peak power pulse before you had enough average photocurrent. So, yeah.
Thank you.
Yeah.
Thank you. I have a question related to this one. So to me, the shot noise is always related to the number of photons, right? So when you say that you reduce the pulse duration and reduce the shot noise, what about the number of photons in this pulse? Is it the same? Then I'm surprised. If it's reduced, then I'm not.
It's the same, yeah.
But then it's surprising.
It's a little surprising, yeah. So yeah, I mean, we tried to capture that. You know, you should check out the paper. There's a few other analogies in there. We try to capture that is that like here's the noise of the long pulse, and it's kind of spread out over time. Here's the noise of the short pulse, it's bigger, right? And so the area here is the same, but in the zero crossing in the quadrature, the region that is sampled is smaller, the product here, and that's what this bottom trace exhibits, is that you have a bigger multiplier of the noise when you're looking out of quadrature here with the longer pulse. So maybe that's the reason why the integrated noise in this short pulse is less. Yeah, it is strange.
I'm still surprised.
Yeah.
Thank you very much for this great talk. I mean, my question is very general. You have combs in optics. That's a good thing. You have a lot of applications with that. You can do spectroscopy and stuff. But what if you have a comb in the RF domain itself, which spans about, like, let's say 2-3 gigahertz, and the rep rate is on the kilohertz level? Do you see any practical applications of these combs?
I think, yeah, that's a good question, and I get that question a lot, or not a lot, but often. And I think, like, because people, you can make RF combs, like these existed long before optical frequency combs. And the unique thing about the optical frequency comb, why it's so special, is it provides that link between the optics and RF. We already have techniques in the RF domain to count and to measure those fields very well, but we didn't have the similar techniques in the optical domain. So that's what's really unique. And that's not to say that RF combs aren't useful. There's people exploring like acoustic combs also in optomechanical systems, which are actually, it's a very fascinating field. But what the optical frequency comb does is it provides this phase coherent connection, and that's what it's really useful for. So I think RF and optical, RF combs are, a strongly driven diode, right, can provide this. So they're useful, definitely, but not for making this connection.
Thank you.
I have a question regarding the topic. What role does the wave particle model play?
Oh. Yeah, I have to punt on that one. What role does the wave particle model play? Can you say play in what? In frequency comb generation or in?
Both.
I think, I guess sorry, I still didn't totally understand the question, but I think, these are classical fields, and so we're doing experiments with lots of photons. And so in general, I approach the topic from the wave point of view, I would guess. And then, yeah, the noise arises kind of semi-classically in the description of shot noise, I think. That's how I look at that, yeah. Sorry, I don't have a better answer to that. It's probably deeper than I'm able to think.
Thank you.
Yeah, so you talked about lots of different experiments, and I imagine that the actual experimental platform is maybe different here and there, but could you say something about the classical, boring instrumental noise that you probably have to work hard to get to kind of get under control before you do the more interesting things?
In the case of the squeezing, we, all the measurements were done at a high for offset frequency where the laser was shot noise limited. So there, it was actually a very nice laser that came from this company, Menhir Photonics, and their solid state laser, they're really quiet at 10, 20 megahertz off the carrier.
Okay.
So
and you don't have to worry about environmental issues.
Those are really nice lasers, yeah, for those measurements. And yeah, that one was a gigahertz. There's some at 10 gigahertz at 100 megahertz. I'm sorry, yeah, 100 megahertz range. I will mention, like, this problem, this problem is very technically oriented, and we spent a lot of time beating down noise to get, there's noise in this optical cavity. That's the thermal noise, just the Brownian noise of the mirror coatings, right? And that provides this slope here, and that can be pretty well controlled. This 1 on F detector noise is a bit of a black box. I don't know, probably recommendation to PhD students if the advisor says, I want you to explore 1 on F noise as your thesis. You might be here a long time just by the nature of noise. So this one though, but the detector, what really gets us there is an amplitude, like this happens in this regime of, 100 hertz, kilohertz, tens of kilohertz. It's the nonlinearity in the detector, and there's amplitude to phase noise conversion there. So there we need really quiet, really low noise, amplitude noise on the lasers. So that's been a hard practical problem we've had to battle for many years. To get to, the shot noise limit, and sometimes I just show them, I could present a plot with all the details there, but there's often some RIN noise, residual intensity noise on the lasers in this region. This turns out to be this region is very important for radar and sensing applications. So that's why we really work on trying to get the noise down here. But for the squeezing measurements, those are great lasers. I could tell you more if you wanted. Yeah.
Thanks for the talk. I have a question on slide 36.
36, oh, you took notes. Okay.
Did the electronic signal after the homodyne detection?
Yeah. Sure.
Can you clarify more on the noise part? Because you measure the noise somewhere else where you don't have the signal on.
Yeah, so in this dual cone picture, okay, the interference of each pair of cone modes, by changing the repetition rate and the offset frequency, we can make that interference occur at a certain RF frequency. So that's what we do here is we choose a frequency, maybe it was around 20 megahertz or 30 megahertz, where we place the signal, and that's the signal that is this interferogram. But it's all coming out of the same detector. So then we just use a combination of filters. First low pass filter, we get rid of this, a gigahertz laser. So the low pass filter is like a 500 megahertz low pass. And then, yeah, we split the signal here, and this noise gram, actually the noise gram goes with this. We're just looking at the broad shot noise in a certain region of the spectrum. Does that help?
Yeah.
Yeah, okay.
Are there any other questions? There's one online if you would like to unmute yourself also. Otherwise I can read it.
Hello. Hi. Can you guys hear me?
Yes.
Yeah.
Very, very nice talk. I want to shift the focus slightly towards terahertz domain. I'm just curious, especially with the advent of Kerr micro resonators, we have access to very high repetition frequency combs now. So do you see something like dual combs, which results in terahertz combs? And just curious about that.
Yeah, I think what I've seen in the literature that people are doing is they're making the microcombs with maybe a few hundred gigahertz of mode spacing, and then if you have an appropriate photomixer, you can convert that into terahertz signal by optical rectification. And so there's definitely work in that area. I haven't done work in that area, but people are making, and then you can, of course, if that optical rectification process is broadband enough, you can create a comb of terahertz frequencies. Yeah. And so people are doing that and doing spectroscopy and measurements in that area as well. There's also people who are directly generating combs in terahertz quantum cascade lasers and making frequency combs with like 10 gigahertz repetition rate, but centered at kind of terahertz frequency. I think Jerome Feist and researchers at MIT, David Burkhoff, who's now at UT Austin. Yeah.
Okay, thank you.
Sure, yeah.
Okay, I have one more question there.
So going back to this, maybe triggered by the terahertz question, in the community that works with terahertz spectroscopy, they usually work as very low repetition rate. So 1 kilohertz, the scheme, when they measure one probe scheme, they always do it mechanically. They scan the pulses mechanically. The dual comb there would be great for sampling, right? But at 1 kilohertz, is that possible technically to generate 1 kilohertz combs that is stable that can be used for this scheme?
I mean, I saw the work from Akira Ozawa and Thomas Udom. I think they had, with pulse picking, they had, I don't know how low they went. Around 100 kilohertz is what I'm remembering. Maybe not one kilohertz. Maybe it was 10 kilohertz they got in that regime. Okay. So I guess it is possible, yeah. Then you would definitely want dual cone because you wouldn't want to mechanically scan. It's maybe a question of like how much resolution you need, right? I mean, I think there are people making electro-optic, maybe a better approach is with electro-optic combs there, because I could give you some references, but you can't cover as broad a bandwidth, but you could make a very dense comb if you had really high resolution spectra you needed to look at quickly. Yeah, sure.
Okay, are there any other questions? Because if not, you can also address the questions later during the coffee break. And let's thank our distinguished lecturer again.